Ladies and gentlemen, welcome to video 30 in a series of video lectures which are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in late 2017. Today is December 21st in the year 2018, about a year later. The current video number 30 will be the final last video in this series. In this video we will be through with the investigation of the spatial distribution of sunspots, and we shall introduce an isotropic case, which is an idealized case for the statistical characteristic distribution of sunspots at the solar surface. Finally, we will, in a few words, propose a general conclusion to this series of video lectures on the Fivefold Sun project. In this video, we start with a brief recap of the two previous videos dealing with the numerical sunspot distribution, introduce some objections and try to refute them, introduce the isotropic case, and finally we will attribute the found distribution to persistent longitudes. First of all, recapitulating videos 28 and 29, in which we've shown many statistical results drawn from consideration of the archives of the Uccle Observatory in Brussels and the archive of the Kanzelhöhe Observatory in Austria, I want to thank Dr. Klett from Brussels at the Uccle Observatory, who is also the head of CILSO, and Dr. Putzi at the Kanzelhöhe Observatory for helping me accessing their archives and understanding the contents of their data. Thank you very much. We saw in the previous videos that the characteristic counts of sunspots, when average considered over several solar cycles, can be proposed to be as follows, adjusted for a total of 120 spots, which seems to be characteristic for the peak of the solar cycle. And if we divide by 2, we arrive to this numbers of B-poles for the distribution of these B-poles among sunspot groups. There is an equivalent number of 60 B-poles per solar hemisphere, as expected from the solar cycle kinematic in terms of differential rotations, which was introduced in part 1 of the Fivefold Sun as a book and in the first few videos of this series. This is how the numbers of B-poles are suggested to be spread among the top 10 most numerous sunspot groups at the surface of the Sun about the peak of the solar cycle. We saw that these numbers of B-poles approach the numbers of solar ball turns and laps in the kinematic of differential rotation as found in part 1, and it so happens that they are also well approached, rather well fit by the sequence of the divisors of the number 120, which are also divisors of the number 144, which is the number of rigid rotations of the Sun over the Schwabe cycle. These are the divisors of 120, which are not multiples of 5. A few objections can now be considered. First of all, is it correct to propose an equivalence of the number of spots or B-poles seen on the solar disk with the numbers seen on one north or south hemisphere? Of course, physically it is not correct. The western hemisphere cannot be subsumed as under a north or a south hemisphere, obviously, But in the case of a solar disk, we have a hemispheric surface, the surface of which is identical to the surface of a north or a south hemisphere. So if you think of it, you will maybe arrive to the conclusion that we propose that it is in the long term statistically correct to assume this equivalence. Now, is it correct to assume the equivalence 2 spots equals 1 bipole in any sunspot group? Of course, physically it is not correct in any individual instance of a actual sunspot group of more than 2 spots, because it is well known that large sunspot groups counting dozens of spots consist of a major bipole, a major set of 2 spots having opposite polarities, and the other polarities for the other spots are not statistically known and may well differ from half and half of the opposite polarities. However, it is proposed here that in the long term, statistically over many sunspot groups, this equivalence has to be statistically verified. Is the equivalence of observed counts with idealized counts, as proposed in the 2 previous videos, correct or even realistic? Of course, we do not suggest that the numbers, the statistically representative numbers of sunspots and bipoles are exactly those of the solar sequence, which replicate, which represent the numbers of turns in a differential rotation cycle for the Sun. Also, we do not suggest that they actually exactly represent the divisors of 120 and 144. But we do not know which is true. It is very well possible that the here suggested statistically representative counts of sunspots are in fact not representing exactly the true counts. It is, after all, possible that, for instance, the solar sequence numbers, the differential rotation numbers, may approach the true numbers. In order to decide, it will be necessary to investigate a much larger database. Finally, we will introduce a so-called isotropic distribution of sunspots. Of course, it is not to be understood as being isotropic at the solar surface. It is, in a way, in a restricted way, a spherically symmetric distribution. And we call it an isotropic distribution only because we propose that it is the result of an isotropic distribution of the vertices, the icosahedral vertices, which, as we suggest, translate into activity vertices, of which there are 12, including the 2 poles, and isotropically distributed at the solar surface, of which 10 are in the toroidal region. These are the contents of the 8th section of part 6 in the Fivefold Sun as a book. Here are the parsimonious assumptions. This is given here for the record. Please have a look at it if you wish. I will not go into it now. And this is now the description of the isotropic case. We now go briefly into the structure of this this proposed solution. You may have a look at it later. I will just make it clear how it is structured. A, B, C to J are the codes for the faces, the 10 toroidal faces of the icosahedron. Here in the top half, the north hemisphere distribution, in the bottom half, the south hemisphere distribution, and here for the whole Sun, the sums of north and south. Here in this column are given the contents of each row. These are the bottom 5 sunspot groups in this row, i.e. The 5 groups which have each the least number of spots, whereas here we have in this row the top 5 groups in terms of how many sunspots each has, and below we have the numbers of B-poles. In fact, in this table no sunspots, but B-poles are given. B-poles for the bottom 5 groups, B-poles for the top 5 groups, and a total for the 10 groups in the north hemisphere. Same for the southern hemisphere, and then for the whole sun, north plus south. Here are boxed in the whole sun part the faces for which the sum of the B-poles is largest. And you see we retain a threshold which yields 6 such groups. We will show later the implication of the fact that these two are adjacent, and J returning to A is also adjacent, are mutually adjacent faces, whereas in the other cases we have alternate faces, which are the faces with the largest numbers of sunspots. Now you see the same table now, but the characteristic numbers of B-poles are replaced by idealized solar sequence numbers. I go back to the previous page, where you see, for instance, that in face A, the number 1 group in the north hemisphere has characteristically, as found shown in the previous videos, 22.5 B-poles, i.e. either 22 or 23. Now, if we go to the equivalent for solar sequence numbers, we have exactly 23, because this is a solar sequence integer. It turns out that if we want to implement the isotropic assumptions in the case of solar sequence numbers, integers of this sequence, we have to find here in orange rounded numbers of exactly one B-pole, i.e. 2 spots in many cases, which is of course a drawback, making this idealized solution somewhat not as realistic as would be expected. Now we show the idealized case with divisors of 120 and 144, in which you see when we had 23.5, I show again the characteristic numbers, 22.5. Here we have 24, because this is the integer which is the divisors of 120. And in this case, the unrealistic part is that we have a few cases in which we do not have a number to be attributed, a number of B-poles to be attributed to one of the top 10 sunspot groups, because we have only 8 such divisors. We will now show on the 3D model how this distribution translates in the 3 dimensions. So this is the 3D model which you saw a couple of times before in earlier videos. A spheroid comparable to the solar ball, the surface of which are now drawn the edges of a concentric icosahedron. The triangles that are drawn in one of the faces, in the front face here, were used earlier to show the size of the characteristic sunspot group surface area according to McIntosh 1992. The size of this green circle. The red sticks correspond to face centers. There are 10 toroidal faces with 10 face centers shown as red sticks. Now, in this 3D model, are represented sunspots by pins. The black pinheads represent sunspots as characteristic numbers of spots from observations as discussed in video 29. Whenever there are red pinheads, these represent the possible additional sunspots in each group, which are predicted by idealized number, either an idealized solar sequence number or an idealized divisor of 120. Plus 2 represents the additional number of idealized sunspots in either case, so either a total of 44 or 46. If we now look in the southern hemisphere, we have a set of only 2 sunspots, i.e. just 1 bipole. We turn now to the next phase, icosahedral phase, in which we find now in the southern hemisphere a set of either 16 observed or 18 idealized in one case sunspots in the southern hemisphere. In the northern hemisphere we have just 1 bipole. We now turn again to the next phase, where we have no large sunspot in either hemisphere. Again to the next icosahedral phase, in which we have in the southern hemisphere a set of 24 observed sunspots plus 4 sunspots maybe as idealized, and in the northern hemisphere just 1 bipole, 2 sunspots. We now turn again to the next phase, and we have in the northern hemisphere 12 observed spots plus in red 2 potential idealized sunspots, and the southern hemisphere again only 2 bipoles. And now we arrive to the opposite face of the first face that was shown as a front face, in which we had the largest sunspot group of the northern hemisphere with 44 or 46 sunspots. Now, in this opposite phase, this largest group is in the southern hemisphere, so this group is antipodal to the first group that was shown for the northern hemisphere. So we have the 2 largest groups in antipodal positions in this isotropic solution. We turn again and arrive at a phase in which we have just 1 bipole in the south and a rather small sunspot group in the north. And now again a phase with relatively few sunspots in the north and in the south. Here now we have a phase with either 24 or 28 sunspots in the north and only 1 bipole, 2 sunspots in the south. And the last phase, icosahedral phase, with either 12 or 14 sunspots in the south and only 2 bipoles in the north. And we are back to the front face that was shown first. So you see, this is the suggested isotropic solution, in which we have sets of antipodal groups which are matched in size. We now turn to the attribution of these groups to persistent longitudes in the Sun. In this second and last step, we now try to attribute the distribution of sunspots and bipoles in the isotropic case to active longitudes detected in part 2 which we can call now here persistent longitudes, because we saw in part 2 that there is evidence of their presence as way back as during the Maunder minimum and somewhat earlier. So we do not have only active longitudes for one or a few solar cycles, but across dozens of solar cycles. These were the found estimates for the Carrington longitude of these spatial alignments, and this is the sixth place, which is not the same in odd and in even cycles, apparently based on the limited data at hand. So these would be the permanent or persistent locations of persistent sunspot groups. These are the total whole sun counts of bipoles across the 10 icosahedral faces, and these are the six main sunspot totals for north and south hemisphere in these phases, and which again we saw that there is a phase alternation in this distribution, with this exception and the exception between J and A. Here we attribute arbitrarily the Carrington longitude 125 degrees to phase A, its center, and we add 72 degrees, and in the two exceptions 36 degrees. In fact, we used 125 because we know that the observed estimate for the corresponding active longitude is 120 degrees, and 125 by trial and error approaches perhaps a best fit for the rest of these longitudes. So you see there is here indicated the variance between longitudes as observed and longitudes in the isotropic case, starting with 125 degree Carrington longitude. And we see that we have little discrepancies, less than 10 degrees in each case, except for this sixth longitude, which is difficult to attribute to a specific place in the sun. We show now the attribution of these longitudes to the sunspot groups in the isotropic case, as shown earlier. We now use the same 3D model as just before, except that is now shown, in addition to the sunspot numbers, the longitude which is attributed to the center of the face in which the sunspot group is located in either hemisphere. We show first the front face with the largest number of sunspots, so-called group number 1, for the northern hemisphere, and you see that the attributed persistent longitude is 125 degrees with a spacing of 72 degrees between faces, and below 120 degrees, which is the detected actual location of the persistent longitude in observations. We turn now to the next phase, in which these longitudes are respectively 89 degrees and 80 degrees. The next phase is not an active, corresponds to no active longitude. And this one is the problematic longitude, which apparently is different in odd cycles and in even cycles. So there is a wide margin of uncertainty. The next phase does not correspond either to an active longitude. And now we arrive to the antipodal sunspot group number 1 for the southern hemisphere, which is located at a longitude of either 305 degrees or 310 degrees. The next one again is an active longitude that is detected in observations, but you see it corresponds to a rather small whole sun number of sunspots in the corresponding icosahedral phase. The next phase does not correspond to an active longitude, and the numbers of sunspots are small. And then again we have an active longitude detected at 190 degree Carrington longitude, corresponding with the spacing of 72 degrees between phases to 197 degrees in this proposed isotropic solution. Then the next phase does not correspond to an active longitude, a very small number of sunspots. And we are back to the front face that was shown first. So these would be the persistent locations of the main sunspot groups across many solar cycles and centuries. This is time now, ladies and gentlemen, to propose a few words of conclusion on the Fivefold Sun project as a whole. We reviewed the cycle kinematic and found Fibonacci numbers for rigid rotations. We found the number of 60 laps, which is part of the so-called solar sequence of generalized Fibonacci numbers, each of them corresponding to a set of rotations in the differential rotation of the Sun. And we found that the number of total number of rigid rotations across the solar cycle is statistically 144. Then we found that the intracycle quasi-periodicities observed by many authors correspond to Lucas numbers of rotations, which are also generalized Fibonacci numbers. We then turn to the three-dimensional constitution of the solar ball, and we found that the size of the core and of its envelope correspond to icosahedral radii. This entails that the radial structure of the Sun can be reconstructed using 12 balls, so-called outer balls, which are tangential to the energy-generating core and tangential to the circumscribing photosphere, 12 happening to be the root of the number of rigid rotations, 144. In part 2, we also found that there seem to be 5 activity vertices per hemisphere in the Sun, as many as the vertices of an icosahedron. In part 6, we found that at the surface of the Sun, the sizes of the surface cells corresponds to a cascade which we can predict from an icosahedral dissection of the solar surface. And finally, we found in the last few videos at the solar surface as well that there are indeed 60 bipoles characteristically as expected from the 60 laps according to a sort of a Babcock model of differential rotation winding of magnetic field lines. 60 is the sum of the solar sequence differential rotation. Finally, we saw in part 2 and in part 6 that the main sunspot groups are located at the at the centers of the faces of a concentric icosahedron in the Sun, i.e. at a latitude of 20.9 degrees. As found by many authors in the late 19th century and confirmed rigorously more recently in Korea by Chang. These groups are longitudinally spread according to the distribution shown today. As a result, we propose that there is reasonable evidence that there is a fivefold solar constitution in space, in volume and in surface, and there is a fivefold solar kinematic over time. The Fibonacci numbers of rotations, Lucas numbers of rotations, and solar sequence numbers of rotations all stem from the mean and extreme ratio, which is fundamentally associated with fivefold symmetry. Remains to be explored a set of exceptions, in fact, to this suggested fivefold symmetry. The cycle length variability may be associated with a varying number of outer balls in the Sun, if it is true that the characteristic outlying lengths are 169 rotations and 121 rotations, and that the roots of these numbers may correspond to a variation about the icosahedral value 12. Secondly, another exception is there, in fact, as suggested in the Fivefold Sun and in this series of videos, a poloidal cycle which is offset versus the sunspot cycle, not always an antiphase. Also remains to be explored many mysteries of the long period behavior of the Sun. We found that there is actually, as already suggested by previous authors, at least one period doubling and maybe two period doubling sequences of oscillations in the Sun. Why is this the case? Are the beats between varying quasi-decadal cycle length perhaps the key to this phenomenon? Is there a solar sequence, a set of long-term oscillations of which is suggested here that the 208-year Suisse de Vries cycle is a manifestation? Finally, for the H-Faber set of cycles, the H-Faber pulsation, it is currently perhaps interrupted. It was interrupted during the Maunder minimum. Why is it so? Is it perhaps a break after 3 cycles, or is it a break after the hemispheric lead reversal, which is found to happen after 4 cycles? This is, ladies and gentlemen, the end of video number 30 and the end of the series of video lectures pertaining to the Fivefold Sun as a book, companions to this book. You will see in addition another video, so-called Visio 0, in which is the table of contents of these 30 videos. I thank you for your attention.